So we are now into the introduction of another bioinspired optimization technique, which is known as Dolphin Echolocation Algorithm. This algorithm mimics the way dolphin look for its food. So whenever it detects what it does is it emits some sound signals randomly 360 degrees around itself, and whenever it detects some prey like small fish, what it does is the frequency of this sound wave get increased. So what happens is, if if this is the dolphin, in the first instance it emits sonar signals. Sonar means sound signals, and this sound signal travels, and whenever this sound signal detects some prey means small fishes or anything that is in the menu of the dolphin. What happens is those sound signals get reflected from the body surface of the prey, and it travels back. And due to some organ inside the dolphin, this dolphin can understood that whether it is a prey or it is something else. Now once it understood that this is a prey, it starts to emit this signal at a more frequent manner. We say it as click. So once it detects a prey, the click rate get increased, and slowly and steadily the dolphin understood the shape, size and characteristics of the prey. It is very similar to the way bat or whale detect its prey. Bat also do the same thing, it emits sound signal. Whales also do the same thing, it emits sound signal, not detect, it emits sound signal, and when it gets reflected from an object, and when it is reflected from a prey, it can differentiate the two reflection, and when it detects that there is a prey, it starts to radiate the sound signal more often, and to that specific area to approximate the shape, size and characteristic of the prey. And at the first instance, the dolphin emits its sonar signal to every direction randomly, but once it detects the prey, it starts to emit the signal at that direction only, and also at a higher rate. So the dolphin, bat, whale, all follows the same method of food foraging. By food foraging, we mean the way it searches for food. And what happens if there is a single dolphin, then it depends upon the sonar signal emitted by itself only. And if it is a team of dolphin, then what happens? They show a swarm-like characteristic where what it had does is once any one of the dolphin within the swarm detects the food, uh, it it starts to emit the sonar signal at a more frequency and at the direction towards the prey, and it also emits a signal towards its co-dolphin or the partners of the swarm, such that the members of that swarm also starts to emit its sonar signal towards that direction of the prey. So what happens is when both or most of the members confirm that there is a prey in that direction, then the chance of getting the prey is increased. So the probability of availability of prey at that direction also get increased. So the entire swarm starts to swim at that direction only. But when the dolphin is hunting on its own, then also the system is same. But the only thing absent is this confirmation. So this confirmation actually helps the dolphin to increase the probability of getting a prey on that direction. If there is no other dolphin, then it has to rely on itself only that there is a prey in that direction. So that is all. But in this algorithm, Dolphin Echolocation Algorithm, which is in short it is DEA, we will consider only one dolphin only, or the food foraging behavior of a single dolphin only. So this Dolphin Echolocation algorithm is also a part of the bio-inspired optimization technique group membership. If you are a group member, then you will get this for free. But if you are not a group member, then you must be a subscriber of my YouTube channel or my newsletter Hydro Geek, and you can scan the QR code to access the membership portal. So these are all the background information of dolphins and echolocation. So just go through it and I will come back again when the optimization problem is given to you. So this is actually expansion of how dolphins produce and receive sound waves, and I have said earlier about the clicks and the ear sacs. By this is the I say that they release a sonar signal, and when it gets reflected from its prey, it can process that reflected signals by some special organisms which is available inside its body. So this is ear sacs. There is ear sacs which vibrate and create the clicks that are emitted through the dolphin's melon or fatty organ in their forehead. And this, what it will vibrate is when the ear sacs is vibrating, the sound signal is generated, which is actually referred as clicks. And these clicks can then travel through water and bounce off objects, returning as echoes. So, they are received by the dolphin's lower jaw, which is filled with acoustic fat and sensory cells. Now, these acoustic fat and sensory cells actually process the signals to accurately perceive their surroundings and locate prey or navigate through the complex environment. So you can understand with the help of this ear sac vibration, it generates the sound signals or sonar signals, which is also known as clicks, and it emits it through the something known as melon, a fatty organ in their forehead. And when the signals get reflected from either from prey or from some other structures, it is received by the dolphin's lower jaw. So the signals are emitted from the forehead. This is the signal emitting area. But when the signals get reflected, it is received by something, some organs, some acoustic fat and sensory cells located in the lower jaw. So which actually process that whether it is a prey or it is a structure, right? Now, so here it introduces how the Dolphin Ecolocation Algorithm can be applied to numerical optimization. So this study means this introduction to this Dolphin Ecolocation Algorithm. So this is the optimization problem. Minimize y is equal to x square when x is your design variable, and x can vary within 0 to 1, and x should be a real number. And this entire y is equal to x square is the objective equation. Here our objective or desire is to minimize this equation, and we can change x, this design variable, to optimize or to minimize y. And this x can vary in between 0 to 1, but it cannot get the value of 0 or get the value of 1. So this is the optimization problem. So what is given here? in case of Dolphin Ecolocation algorithm, this is the start of Dolphin Ecolocation algorithm, because this problem of y is equal to x squared, this benchmark equation, is a common equation that I am using for demonstrating the other bio-inspired optimization techniques also. But here what happens, as you can see, that number of design variable is x. So in case of Dolphin Ecolocation algorithm, they represent design variable by j. This is j. So this is j. J is the number of variables. Here there is only one variable, so j will be 1. But it may happen there are multiple variables. Suppose x1, x squared plus x2 squared plus x squared. If there are more than one design variable, then j will be 1, 2, and up to n. Now, here also there will be a fitness evaluation medium. And as we are trying to minimize the objective equation y, so our fitness medium will be this one, yi plus 1, that means the new y must be less than the old y. But here, what happened is I am saying here ith value of x, yes, ith value of x is there. But the thing is that later on I will show that here I is actually the number of location or population or alternatives. Okay, so I will come back to this, but what we want is that our y at every iteration will be less than the earlier y, the y at the earlier iteration. So, however, in this algorithm, we represent iteration, number of iterations, as loop, and we use the variable k to represent the iteration number. Okay, and we use the variable I to represent the number of location, population, or alternatives. Okay, so here fitness evaluation medium means I plus 1 is the new location and yi is the old location. So new location must be, the y at new location must be less than the y at old location. Then only it is fit. If it is not, then we have to think something else. So here the search space is nothing but the constraint domain, lower bound to upper bound. So here the constraint is x is within 0 to 1. It cannot take the value of 0 or cannot take the value of 1. So the lower bound to upper bound is your search space, where you can randomly select values of x. The only thing is that you cannot take the value of 0, you cannot take the value of 1. And in case of DEA means the Dolphin Ecolocation Algorithm, you can take only the 1/4 of the entire search space to collect your values of x. Okay, so 1/4 means you can take any value from 0 point something to 0.25. Okay, and they said that minus RE, the radius of searching domain, lower bound, actually for our case will be 0. plus array, this is the upper bound, minus means lower bound, plus means upper bound. So the lower bound would be 0, not 0, actually more than 0, and the higher bound will be 0.25. But note here you can take the value 0.25 also, because it is far lesser than 1. You cannot take the value of 1, but you can take value of 0.25. So the advantage of this reduction of search domain is that only those values of x will be taken which has a higher probability of generating a more optimal solution to the given problem. Okay, so these will be given the number of design variable, as I've already said, x. For our case it is x only. And fitness evaluation medium, new y must be less than the old y. Y means the objective function, and as our goal is to minimize the objective function, that is why the previous y or the new y will be less than the previous y. But noted down, in many algorithms, I is your number of iteration. But here it is not so. Here I is the number of location population alternative. What is that number of location population alternative? That I will discuss later on. But I is not your number of iteration. Here the iteration or loop is referred to as k. Okay. So another modification which is not found in the other bio-inspired optimization techniques is, although your search domain is from 0 to 1, but you can take only 1/4 of this search domain for generating your values for optimization for your design variable x. So that is why this will be 0 to 0.25. Okay. So now let us take you to the what are the assumptions. So the assumptions are, first of all, please again note down that in this algorithm, assumption depends upon you only, the user only. Okay, you can change number of location or population. That means at the initial iteration of the first loop, what happens is with random, as is the case for other meta-heuristic optimization algorithm also, we randomly generate 4 different values for x or our design variable. So in case of DEA or Dolphin Ecolocation Algorithm, these 4 locations is your number of location or population. So if you remember or if you recall, I have said at the first iteration, Dolphin used to generate its sonar signal randomly in the 360 degree of its search domain. If this is the Dolphin, so it can generate its sound signal 360 degree and in a random manner. There is no pattern in it. So these are the direction that you can say that the sound signals have been generated. So these are the 4 random values of x that was generated in the first iteration. But if you wish, you can generate more random signals also, or random locations also. If you generate more random location, then your rate of convergence will increase. But it also happens that it will take a lots of computational space, and for that you need to use supercomputers. And also, as the requirement of computational space is very high, so what will happen? The rate of iteration will, after all, get reduced. Now this is the number of loops. That is why I am saying here number of location and number of loops is different. Here I is your number of location, okay, not the number of iteration. If you say what is the iteration here, you will say iteration means a loop, because this is a loop-like algorithm. Until we get the optimal solution, we continuously repeat the procedures. So generally for one-dimensional problems like this, like our case y is equal to x square, where only one design variable is there, we take 50 number of loops. Yes, of course we can take more number of loops, but it will only lengthen the optimization. But yes, for complex type of algorithm, multidimensional algorithm, optimization. By multidimension, I am saying that when x is also again a function of x1, x2, and so on, then you must increase the number of loops to up to 2000 also. But here also the same thing happens. The more the number of loops, slow will be the optimization rate, because of the utilization of computational space at a more frequent rate than where the loops are low. Now here convergence factor is assumed to be 56% or 0.56, and this is a E, this is an error which will be minimum of minimum value of fitness. For every iteration it will be assumed accurately. Okay. What is this? I will come at a later stage. So here you have to assume this fourth thing, number of location or population, that is the number of values you will generate in the first instance. Values means x, right? So how many number are you are generating here? 1, 2, 3, 4. So here I is 4. Okay, and for each x we will get a y. For each x we will get a y. Okay. Okay. So now let us go to the next step. Now calculate at each iteration. Remember here each iteration I am saying, actually it will be calculate at each new location, that means I, and also for each iteration. So what happens is, for each iteration or each loop we have 4 values or 4 location. Okay, so you have to calculate it for those 4 location per iteration. Okay, so if you are doing 50 number of iteration, then for each iteration 4, that is 15 to 4, 200 times you have to calculate. Clear? So what you have to calculate? The fitness I. Fitness I means at each location x1, x2, x3, x4, you will get y1, y2, y3, y4. Because y is actually x square. And this randomly generated value x1, x2, x3, x4, you are putting here y is equal to x square, and a new value of y is generated. Okay, so if I say that this is the initial value of y is, say for example y k, and if the new values of y is like this, y I is equal to 1, y I is equal to 2, 3, y I is equal to 4. So you have to compare this yk with each of these new y's, each of the new y's. Okay, so that will be your fitness at I. And that fitness is, as usual, the old y what happens is the old yk must be less than the new i's, yi, which is equals to 1, 2, 3, 4, whatever number of location you have decided to take. And this must be is less than 1. Okay, so the frankly speaking, among these yi's 1, 2, 3, 4, you will check which one is minimum y. And then you compare that minimum y with this old y. Okay, and if the minimum y of the among these 4 population, if that minimum y is lesser than this old yk, then you go with the new y. Otherwise, you go with the old y. Okay, or yeah, that is what is the case is. Now, this is the fitness. Second thing is accumulative fitness, AF. So for each of these y, you have to calculate the accumulative fitness. How it is calculated? AF, accumulated fitness at A. This is actually A means they often say it as number of alternatives. Why they say it as alternatives, I will discuss about it later on. For now, you just take it that A is your number of location, and A can be said as I. Okay, I is your number of location, so A is your number of location. So at each of these i's, or for each of these y, for the 4 number of location that you have generated, you have to calculate this AF. So you will have total 4 AFs. And how you will calculate? You will calculate by this 1 by RE. This is the search radius into multiply your radius minus total number of loop, or total number of loop, I would say, to avoid confusion, K. What is the fitness? I. Correct? Plus AFA plus K, J. So what happens is that for each of the value of this I, what we do is actually what is 1 by RE first you say. 1 by RE is yours 1 by 0.25. Correct? Now multiplied by, again this will be your 0.25 because this is plus RE. Okay, this is plus, this is plus. So as I have discussed in the previous slide, plus RE is for our case 1/4 of the search domain. So it is 0.25. Now if it is the first instance of the first loop, okay, then this K will be 0.01, because you cannot take the value of 0, so you have to take something greater than 0. So this K will be your 0.01, and this fitness I will be your minimum value of Y. Okay, the minimum value of Y among this 1, 2, 3, 4. When you compare with all these 4 Y's with the old Y, and if you get that among these 4 new Y's is the minimum Y. I am sorry, this is not the case. For fitness I, for each of the Y will be the value of the Y. Let me again mention this. So for Y I is equal to 1, the value of Y for x1 will be fitness I. Correct? Or to be more precise, the value of Y at x1, divided by the old Y will be your fitness. ठीक है, plus AF A plus KJ is your, this one is very confusing because here also AF K plus J, here also AF K plus J. Okay, so what happens is that here you say there's a where A plus K at J, J is the number of variable, A plus K is the number of iteration or number of alternatives or number of population. For each population A there will be one AF, and for each iteration K there will be one AF. For J number of design variables there will be J number of A plus K iteration. So what happens is mainly you have to calculate this part. This part will be 1 by 0.25 multiplied by 0.25 minus your first value 0.01. I think you can understand because this is the first iteration or first loop. So you will begin K from the first value permissible up to the lower bound, and where permissible value is more than 0. So I am taking 0.01. So 0.01, 0.25, correct? Multiplied by the fitness I. Fitness I means the value of y at x equal to 1 divided by the value of old y. Okay, so in the similar manner you will get, as we have 4 number of population, you will get 4 number of AFs. Okay, and here you see that now let us go into the another thing that you have to calculate at each iteration. Up to this calculation of accumulated fitness, just remember for each step or for each iteration you will get 4 number of AFs if you have considered or generated 4 number of location at the first iteration, first instance. For now you can neglect this as 0. Now the next thing, third thing that you have to calculate at each iteration is probability at ith iteration for jth variable. So Pij, this is the probability. Here the things comes very interesting. What is this Pij? Pij is actually the F at each of the y generated here. So there are 4 F, okay, and this divided by 4 into F. That means F at y is equal to 1 plus F at y is equal to 2 plus F at y is equal to 3 plus F at y is equal to 4. If you generated 6 population, then it could have been F y is equal to 5 plus F y is equal to 6, correct? So here there are 4 y's, so you will get 4f, and you have to add all these af with each other, and that sum will be divided from each of the f to find the probability at the ith iteration or at the ith iteration for jth variable for kth loop. Okay, so for when k is 0.01, as I have already mentioned. Now what happens is, another thing to calculate is the predefined probability. So this is the predefined probability for each of the loop or for each of the iterations. You have to calculate one PP, predefined probability. So for the first iteration, what happens is PP1 is your convergence rate or factor. So you take it as 0.54 or 0.56, whatever you may think, plus 1 minus PP1 multiplied by loop I to the power. So loop I means the present loop, current loop. It is the first loop, then it is 1. If it is second loop, then it is 2. If it is a third loop, it is third. Okay, so if it is ith number of loop, then it is loop I. And this power is the degree of linearity. So we do it as power is equal to 1. We take the linear value only, or less than 1. We experiment with the power, but mainly we assume that power is 1. Okay, such that if the linearity is maintained. If you are also trying to consider non-linearity, then you can use power more than 1. Whenever you are using this power as 2, this entire equation become non-linear. Okay, and this loop number is a loop number that you have assumed at the assumption step. For our case it is 50. This power and this power is same, so accordingly you will get the value of the PP, matlab predefined probability at each of the iteration, the real iteration, not the generation. When you are generating this 4 population, we are referring it as I know, but these I is actually indicating the number of generation. But here in this case, Dolphin Ecolocation Algorithm, K is the actual iteration. Okay, and we mention it as loop. Okay, so these 4 things you have to calculate at each iteration. Each iteration means K. So what is the procedure now? Let us come to the procedure. So what happened at the first iteration? I have said K is equal to 1. 4 locations are alternative, that means X, values of X. As I have already discussed, we will generate 4 values or 4 populations. So X5, X1, 2, 3, 4. So because we are generating 4 number of population, 4 location or 4 population or 4 alternatives of the values of X randomly generated at the first iteration. So 4 location or alternatives at the first iteration, K is equal to 1, randomly generated. Randomly generated means within 0 to 1, normal distribution. Okay, any value within 0 to 1. Now you'll say, yes, you just said that we can use only 1/4 of the constant domain. Correct. Any value within 0 to 0.25. And to be more precise, you cannot take 0, you can take 0.012, 0.25. So any value in between these two you can take, and you have to generate 4 number of such values. Okay. Now for each x there will be y. Yes, for each x I have already discussed. For each x there will be y. How y? Y is equal to x square, and our goal is to minimize. Okay. So for each y, fitness will be calculated as I have said. Fitness you must calculate at each iteration the fitness. Okay, fitness for each of the population. Mind it. Here I indicates population. I is 1, I is 2, I is 3, I is 4. But this thing has been generated in the single loop only. Loop is equal to 1. Okay, the first iteration. So this is there in case of DEA, loop is K. Okay. So fitness for each population need to be generated for Y1, for Y2, for Y3, for Y4. You have to calculate the fitness. And for each of the X, you have to calculate the AF. Okay. And then you have to calculate also the PP, that predefined probability, but this PP is for only the number of iteration, not for the number of location or number of population. Okay, so this is the PP. Now what will happen for each X? A will also be calculated. Yes, Pij, probability, not predefined probability, but probability of each I for each variable. J is your variable, I is your number of population. So for each population or for each value of X, you have to calculate one probability. Okay, so and Pij and Pp will also be calculated. So here I have told you incorrect. This Pp is also to be calculated for each of I. I means for each of number of location. Okay, and for each of iteration also. So for to be summarized, you can say for at each iteration k or for each loop k, if you are generating 4 number of locations or 4 number of x, then you have to calculate the fitness, 4 fitness, 4 accumulative fitness, 4 pp, predefined probability, 4 probabilities. Okay, so after doing all this calculation and all this thing, try to identify the minimum value of y among all the 4 y's generated and also the old y. Matlab, what happens is if at k is equal to 1, you have already detected that y is equal to the second population is the minimum. Now you have at k is equal to 2, you have generated again 4 number of y's, correct? So from here also there will be some y will be minimum. Okay. Then compare this and this. If this is minimum compared to this, go with this one. If this is minimum compared to this, then go with this one. But the y at k is equal to 1, if minimum compared to the y at k is equal to 2, then go with y at k is equal to 1. But if that is not the case, go with the new y for the next key. Correct? Okay. So the minimum y among the 4 y's will be the best location because our goal is to minimize the y. If our goal is to maximize y, then the maximum y will be our best location. So for this location, Pij, the probability that you have calculated for each of the population, for each of the variable, for our case, j is only 1 because y is equal to x square, x is the variable. So for each of the variables you have calculated this Pij. This Pij will be equal to Pp, predefined probability, if that y, that means y at I, is the best location. So if it is not the case, then what we will do? Then the probability for the other populations will become 1 minus pp, 1 minus predefined probability multiplied by the probability of that location. So I have already showed you how you can calculate the Pij, that I have already showed that A alternative fitness at that I divided by the summation of all the alternative fitness of all the population will be the probability. So Pij. So this will be multiplied with 1 minus predefined probability and used as the probability of other locations. Okay. Now after all the above step is repeated, now what will happen is until then this step or after this step you go back to the initial step of the iteration. That means you repeat the steps that we have followed from the generation of population. Again you generate 4 population within the constraint search domain, not within the constant search domain, but 1/4 of the constraint search domain that I have already discussed. And then again you calculate those things, Pij, Pp, A, fitness, all these things. Again try to find the minimum y of among all those y and the minimum y of that previous iteration. And that minimum y will be the best location. So for the best location, you assign the probability as PP, right? Pij will be equal to PP, and for other locations, you will assign the probability as 1 minus PP multiplied by Pij. So you continue doing this until the total number of loops that you have assumed in the assumed step is completed, or there is no improvement in the optimal value of y. That means suppose for 10 to 100 iterations, the same y is become the best. Same yi is becoming the best location. So when that is the case, you can stop, or you can stop after your predefined or pre-assumed number of loops is over. That means in our case it was 50. So when we have achieved 50, so as this is the number of loops is 50, so I cannot go to 100. So suppose within this 40 loops have been completed, but for the last 10 loops, same y is coming as the best y. Then you stop it. Or before that, 50 loops are completed. Then also you stop it. So this is the way this Dolphin Ecolocation algorithm is algorithm take place. So this is the way this DEA takes place, Dolphin Ecolocation Algorithm. So with this we conclude the DEA optimization technique, and for a more detail you can refer to the main paper of this algorithm. I will give it into my description or my body of the newsletter. And remember, this DEA is very well suitable for getting the optimal value for multi-dimensional optimization problem, and also it is very fast, and it can easily avoid local minima because of that condition. You can take only 1/4 of your search domain, not the intent. So this assumption actually helps this algorithm to get the or search about the best value of the search domain and detect the optimal value very easily under very short time. So with this I will end this presentation, and my next presentation will be on fish or artificial fish swarm algorithm. So of course kindly subscribe to our BOT Bio-Inspired Optimization Technique group membership. We will continuously add new bio-inspired optimization technique in that membership. And otherwise you can go for our YouTube videos, like, subscribe, or you can subscribe to my newsletter also, Hydrobic. So thank you for your patient hearing.